Hello everyone, I'm Josh Garfinkel, and we are representatives from Opportunity, and here to tell you about our observations of Messier 77, or for our English speakers in the audience, Messier 77.
So this is M77 taken by the Hubble, and I want to go over the composition and the components of the galaxy. So in the center you see a bright white spot which is called the nucleus, and it's primarily composed of population 2 stars and an AGN, or an active galactic nucleus. And it's theorized that this active galactic nucleus is a black hole, and it's so bright because it includes a lot of matter in the form of intense radiation. And usually AGNs outshine the stars within their galaxies. So we thought that a filter that would penetrate the dust would give us a brighter image. So we hypothesized that the Sloan Z filter, which only permits infrared, near-infrared light to pass, would give us a brighter image and a smaller size overall, because you're seeing less of like the dust in the arms, so it would give you a smaller galaxy size. And then we said that the clear filter would place more emphasis on the stars in the galaxy, and the stars in the center would be kind of drowned out by the light from the AGN and the gas there and the dust. And telescopic CCD specifications are listed here, but I'm not going to go too detail about that.
So after coming up with the design for our experiment, we began to observe M77. Over 2 nights, we took multiple frames for the clear and Z prime science images, biases, darks, and flat frames for both of the filters. Our first night was a bust due to an improperly calibrated telescope guidance system, which tracks the movement of the galaxy across the sky, keeps it centered in the image. This led to badly doubled images where everything was distorted and blurry. The second night went much more smoothly technically, but the weather was less than ideal. The high humidity and cloud cover caused the images to be blurred due to light scattering from the atmosphere. After obtaining the photos, the next step was to correct for all of the imperfections that we could. If you wear glasses, you can understand the feeling of minor frustration when the device you paid $200 so that you can see is covered with dust or splotches of liquid, making it so that you can't. If frustration is proportional to the price and difficulty, it's a very different experience when you have to observe within a given time using a telescope that has lens imperfections that you can't just wipe off so easy like you can glasses. So we performed some simple calibration techniques, like using code to account for imperfections in the equipment, such as lens debris, base level noise readouts from within the CCD, and thermal noise due to temperature conditions around and in the electronics of the CCD. Subtracting the master darks and the master bias frame, then dividing by the normalized flat, creates a more accurate and clear image from the original.
So to find the size of M77, we use the area equation listed over there, where A is the semi-major axis and B is the semi-minor axis. And using it for each filter, we got that in the clear filter is 2.1 times 10 to the 4 pixels squared, and for the Z prime filter is 2.7 times 10 to the 4 pixels squared. And then to find the brightness, we did aperture photography and use the same semi-major and semi-minor axis as we did for the previous height calculation. And we used the equation up there to find the flux. And we found that the clear filter was in fact brighter, and it had 8.085 times 10 to the 8 flux in electrons, and while Sloan Z only had 8.4 times 10 to the 7 electrons. So the clear filter ended up being brighter.
In conclusion, what we have accomplished with this project is the successful utilization and testing of these extremely useful calibration and calculation methods, as well as results which have made us have to think about our original hypothesis further. Unlike what we expected, M77 was brighter and smaller in the clear filter. We conclude from this not that our theories are wrong, but that we failed to consider M77 as a Sifat galaxy, or in English, Safart. Sifat galaxies differ from regular galaxies in that they do not have much of a gradual brightening as they approach the nucleus, because the nucleus is far brighter than any of the constituent stars. This means the gas does not pose much of a problem in observing these galaxies. In fact, confining the spectrum to near IR decreases the brightness, as the constituent stars are unable to make up the difference with their infrared light, and the stars and nucleus radiate much less in near IR rays compared to visible light. These findings suggest our present understandings of how dust affects light and our observation of galaxies is in fact correct. Our data can now be used in future research, and photos can be shown as good representations of the M77 galaxy. Thank you.